I want you to try a mental exercise with me for a second. Just picture your neighborhood.
Okay.
The actual street you live on. Maybe it's a quiet cul-de-sac. Maybe it's a busy apartment block in the city. It's manageable, right?
You know the landscape.
You know the neighbors. You know the mail carrier's schedule. You know where the potholes are that you have to swerve around. It feels familiar. It
That
feels small.
It feels contained. I think that's the key.
Exactly. Contained. And for the longest time, I mean, for centuries, really, that is exactly how we treated the solar system.
Oh, absolutely.
We had this quiet street model in our heads.
The clockwork model, yeah.
Right. The sun in the middle, 8 polite planets moving in perfect circles like cars staying in their lanes,
Yeah.
and maybe, a comet swings by every 70 years if we get lucky.
Very orderly, very predictable, safe.
Yes. A nice place to raise the species.
It is a very comforting image. It's the model we all built, out of styrofoam balls and coat hangers in elementary school.
I remember mine.
But it is also, as we are learning every single day, and especially with the data we have right now in 2026, it's just completely inadequate to describe reality.
Completely wrong. Because I've been looking at this massive stack of NASA reports you sent over, specifically the data snapshot of the system as it stands right now in early 2026. And the picture that emerges isn't a quiet suburb.
No.
It's a metropolis. It is chaotic, it is crowded, and it is aggressively dynamic.
That is the fundamental shift in planetary science. We've moved from thinking of space as a museum static, frozen, dusty, to thinking of it as an ecosystem.
An ecosystem, I like that.
It's a construction site that never quite finished. It's a bustling city that never sleeps.
So that is our mission for this deep dive. We are going to conduct a full census of this metropolis. We aren't just reciting the names of the planets like we're in 3rd grade.
No, we're going past the basics.
We're going to look at the staggering numbers of what's actually out there, the architecture that holds this whole crazy structure together, and perhaps most excitingly, what NASA's doing right now in February 2026 to explore it.
And that's the key, the right now part.
Because there is a lot happening.
There is an incredible amount of activity. I mean, we have humans actively training to go back to the moon. We have robots driving themselves, literally making their own decisions on Mars.
That part is just incredible. We'll get to that.
And we have telescopes looking back to the very cosmic ingredients that cooked up this solar system in the first place.
So let's not waste any time. Let's start with the crowded house, the census. Because I think most people, if you stop them on the street and ask what's in the solar system, what would they say?
Well, they'd say 1 sun, 8 planets, and
maybe the moon.
Maybe the moon. And maybe Pluto if they're feeling nostalgic or, argumentative.
Right. But looking at the NASA solar system exploration data, the actual numbers are they're rude, they are staggering.
They break that mental model completely.
Okay, let's establish the baseline. We have 1 star, the sun. We will come back to him or her or it later because that one object is doing a lot of heavy lifting.
It's the boss of the system, no question.
The boss. And we have the 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. We know them, we love them. But then, the dwarf planets.
Ah, yes.
The data lists 5.
5 recognized dwarf planets. And this is a really important distinction that I think people miss. Everyone got so upset about Pluto getting demoted back in the day. There were petitions.
People took it personally, like a friend got kicked out of the club.
They really did. But the reality is Pluto is just the first of a crowd. It wasn't that astronomers hated Pluto. It's that we found its friends. We found its whole peer group.
Oh, it wasn't a weird outcast. It was a trendsetter.
Exactly. A pioneer of a new category. We found Ceres, which is actually in the asteroid belt. We found Eris, Haumea, Make, all out past Neptune. We realized that if Pluto's a planet, then we have to let a dozen other frozen rocks be planets.
Then the word loses all meaning.
It loses its usefulness. So dwarf planet isn't an insult. It's a classification. It means you're big enough to be round. Gravity has pulled you into a sphere, but you aren't big enough to clear your neighborhood.
You haven't swept up all the debris in your orbit. You're a messy neighbor.
You have a cluttered driveway, exactly. Pluto has a very cluttered driveway.
Okay, so that's 5. Speaking of clutter, let's talk about the moons. This number stopped me cold in the report.
I thought it might.
The latest count is at least 290 moons.
At least 290. And counting. Every year we seem to find a few more tiny ones orbiting Jupiter or Saturn.
That is nearly 300 distinct worlds.
And worlds is absolutely the right word. I think we have a massive bias because our moon, Luna, is a dead rock.
A beautiful rock.
A beautiful, very useful rock for tides and eclipses and poetry. But geologically, it's fairly quiet, so we assume all 290 of them are just dead gray rocks.
But they aren't.
Oh, not even close. The diversity within the moon count is arguably higher than the diversity among the planets themselves.
Okay, so walk me through that. If I'm an alien tourist flying through the system, where am I stopping? What are the must-see moons?
Well, you're definitely stopping at Titan, which orbits Saturn.
Yeah.
It's the only moon with a thick atmosphere. Thicker than Earth's, actually.
Thicker than ours.
Much thicker.
Yeah.
And hazy and orange. And it has weather. It has rain, rivers, and lakes.
Water.
No, that's the wild part. It's liquid methane and ethane. It's an orange, hazy world where it rains natural gas into seas of natural gas.
My brain can't even process that.
It is a truly alien landscape. Then you have Io, orbiting Jupiter.
Io, wow.
Io is the most volcanic place in the entire solar system. It's basically a pizza made of sulfur and lava, constantly turning itself inside out because of the immense gravitational pull from Jupiter.
Jupiter's just squeezing it.
It's constantly squeezing and stretching it, which generates a tremendous amount of internal heat. So it's covered in hundreds of active volcanoes.
That sounds intense.
It is violent. And then you have the darlings of the search for life, Europa and Enceladus.
The ice worlds.
Yes. They look like cue balls from a distance, just white, icy spheres. But underneath that ice shell, based on all our data, they have global oceans of warm, salty, liquid water.
And when you say warm,
We mean kept liquid by that same gravitational squeezing, that tidal heating, potentially with hydrothermal vents on the seafloor, just like we have on Earth.
which is where life on Earth might have started.
Exactly. So when we say 290 moons, we are not just counting rocks. We are counting potential habitats. We are counting chemical laboratories. We are counting places that could, conceivably, harbor life.
It's incredible the planets are just the landlords.
And the moons are the tenants living the interesting lives.
And then we get to the numbers that really make this feel like a crowded city. The leftovers, the
Right.
debris field,
The construction rubble.
asteroids. The number in the report is more than 1.3 million.
And again, that's just the ones we've cataloged. There are millions, maybe hundreds of millions more that are too small to see yet.
1.3 million. And comets. The report says approximately 3,900 dill.
Correct. And those are the ones with known orbits. There's a reservoir of trillions of them way, way out in the Oort cloud.
So when you see a number like 1.3 million asteroids, what story does that tell a scientist? Does it tell you the solar system is old? Or does it tell you it was violent?
It tells you the formation was incredibly messy. There's this misconception that the solar system formed like a clock. Everything just clicked into place perfectly.
The styrofoam ball model again.
Right. But it was actually more like a demolition derby.
A demolition derby. I love that.
Think about it. 4.5 billion years ago, there was just a spinning cloud of dust, gas, and chaos. Things were colliding, shattering, sticking together, breaking apart again. The planets are the survivors.
They're the winners.
They're the ones that won the eating contest. They're the ones massive enough to sweep up most of the stuff in their paths.
And the 1.3 million asteroids.
They're the crumbs. They are the building blocks that never got the chance to become part of a planet. Usually because Jupiter, the big bully of the system, kept gravity kicking them around, so they couldn't clump together.
So they live in that belt between Mars and Jupiter.
Mostly. That's the main asteroid belt. They are the construction rubble left on the site after the skyscrapers were built.
But they aren't just sitting there in a pile, right? I mean, they're all moving.
Oh, they're flying.
Yeah.
Everything is moving. It's a dynamic equilibrium. We have this idea of space as silent and still because when we look up at night, the stars don't seem to move.
Right. It looks peaceful.
But if you could speed up time, you'd see a swarm. You'd see 1.3 million rocks dancing and weaving between Mars and Jupiter in the main belt. You'd see comets diving in from the deep freeze of the Oort cloud, swinging around the sun, growing tails, and shooting back out.
It's a beehive.
A beehive. That really changes the mental image. It's not an empty room with 8 chairs.
No.
It's a mosh pit.
A choreographed mosh pit held together by gravity. Which brings us to the bouncer, the anchor, the queen bee.
The sun.
We listed 1 star at the beginning, and I feel like we just breezed past it because, well, that's always there.
We take it for granted.
We do. But looking at the mass ratios in these NASA notes, the sun isn't just the biggest thing in the solar system. It's essentially the only thing.
It is humbling to the point of being insulting to the planets. The sun accounts for 99.8% of the total mass of the solar system.
Okay, I want to sit with that number for a second. 99.8%.
Think about it. Take everything we just mentioned. Jupiter, which is huge. You could fit 1,300 Earths inside it.
A monster of a planet.
Monster. Take Jupiter, Saturn and its rings, all the oceans and mountains and cities on Earth. Take every single one of those 290 moons, all 1.3 million asteroids, all the comets. Put them all in a bucket on one side of a scale.
Okay.
That bucket is 0.2% of the system.
And the sun is the rest.
The sun is the rest. We are basically living in the atmosphere of a star. We are just debris orbiting a nuclear furnace.
So when we talk about gravity,
the sun's gravity is the glue. It is so immense that it holds that Oort cloud comet, which might be a light year away, just as firmly in its grip, conceptually speaking, as it holds Mercury. It dominates everything.
And the notes describe it as a yellow dwarf star, which sounds kind of cute, like a garden gnome.
It's a bit of a misnomer to the layperson, for sure. It's a classification term, a G-type main sequence star. It means it's stable, it's yellow-white in the Beckable spectrum, and it's burning hydrogen into helium at a very consistent rate.
And it's middle-aged.
Pretty much. It's about halfway through its life, 4.5 billion years old, with another 5 billion or so to go before it starts to, change.
Which is lucky for us. We don't want a moody star.
No. Stability is the absolute prerequisite for complex life. If the sun threw a massive tantrum every Tuesday, or if its brightness fluctuated wildly, we wouldn't be here having this conversation. You need a steady heat source to incubate biology.
It does throw tantrums, doesn't it? The notes mention heliophysics and space weather, and there's a headline here about tangled magnetospheres.
It absolutely does. It's not a dead, static ball of fire. It's a ball of plasma superheated gas with an electrical charge.
Okay.
And because it spins, it generates a massive magnetic field. But here's the catch. Because it's fluid, not solid, the equator spins faster than the poles.
Oh, so the magnetic field lines get twisted.
They get twisted up like a rubber band. Every 11 years or so, the magnetic field gets so tangled up that it just snaps and reconfigures itself.
And that's a solar cycle.
That's the solar cycle. And at the peak of that cycle, when it snaps, that's when you get solar flares. That's when you get coronal mass ejections. Billions of tons of plasma shot out into space at millions of miles an hour.
And that matters to us why? I mean, aside from the pretty auroras.
Because we are an electronic species now.
Yeah.
A big enough solar storm hits Earth. And it doesn't just make pretty lights, it can fry satellites.
So our communications, GPS?
All of it. It can induce currents that knock out power grids on the ground. It can disrupt GPS signals that planes and banks and all of modern logistics rely on.
And, crucially for our discussion today, it matters for astronauts.
Exactly. If you're in orbit or on the moon, you're outside of Earth's protective magnetic bubble. If a big solar flare hits, that's a very bad day. It's a serious radiation hazard.
We'll get to the moon and that risk in a minute. But first, I want to map the city. We have the census, the population count. But what's the zoning law? Why are the rocks here, close to the sun, and the gas giants way over there?
It all comes down to temperature. The key concept is the frost line.
The frost line. Break that down for us.
Think of the early solar system as a campfire. The sun is the fire. Close to the fire, it's hot.
Obviously.
So it's too hot for things like water ice to exist. Too hot for gases like hydrogen and helium to clump together easily. So in that inner zone, the only things that could stay solid and build planets were rocks and metals.
So the inner planets, Mercury, Venus, Earth, Mars, they're rocky because that's the only material that could survive the heat.
Precisely. They are the downtown core of the solar system. Dense, compacted, high-value real estate. They're made of the stuff that doesn't melt easily. That's why they're small and rocky.
And then you cross the line, the frost line.
You cross the line, somewhere out between the orbits of Mars and Jupiter, which is roughly where the asteroid belt is today. It gets cold enough for water to freeze into ice.
Okay.
Further out, it's cold enough for ammonia and methane to turn into ices. Suddenly, you have way more building material available. You don't just have rock. You have rock plus all this ice, snow, and slush.
And that abundance of material allowed the giants to grow.
It allowed them to get massive. Jupiter likely started as a big ball of ice and rock, effectively a super-Earth, maybe 10 times the mass of our planet. But it got so heavy, so fast, that its gravity became intense enough to start sucking in the most abundant stuff of all.
The gas.
The hydrogen and helium that was floating around in the nebula. It snowballed, it went through a runaway growth phase, and became a gas giant.
So the layout isn't random. Rock inside, gas outside. It's a direct consequence of physics.
It's a direct result of the temperature gradient. It's the baking recipe of our specific system.
And within those giants, we have a distinction, right? The notes mention Jovian planets, but they also specifically call out ice giants.
Yes, and this is a pet peeve of many planetary scientists. We often lump Jupiter, Saturn, Uranus, and Neptune together as gas giants.
I do that all the time.
Everyone does.
Hmm.
But Jupiter and Saturn are mostly gas. They are primarily hydrogen and helium through and through. Uranus and Neptune, which are further out, are different. They have some hydrogen and helium in their atmospheres, but they are mostly made of ices.
What kind of ices?
Heavier elements, water, ammonia, methane fluids under extreme pressure and temperature. They're less like gas bags and more like giant, slushy, deep oceans.
Yeah, ice giants.
They're the mysterious siblings in our solar system family. We haven't orbited them. We've only ever done a quick drive-by with the Voyager 2 probe back in the 1980s.
That's wild because, as we'll see later, that type of planet might be the most common type of planet in the universe, and we barely know our own.
Exactly. We know more about some exoplanets hundreds of light years away than we do about Neptune's internal structure.
Okay, I love this structure. We have the census, we have the zoning, but I want to pivot from the map to the territory, because this isn't just history. We are exploring this place now.
Oh, yeah.
It is February 2026, and NASA isn't just looking through telescopes. We are there.
We were putting boots and wheels on the ground, or at least preparing to.
Let's start with the big one, the human return. Artemis.
Artemis II.
The headlines in this February 2026 update are very specific. Preparing for Artemis II, NASA selects participants to track mission.
This feels different than the vague promises we might have heard a decade ago. This feels operational.
That's the shift. For a long time, the moon was a goal or a PowerPoint slide. Now it's a schedule. It's a manifest. We have a crew. We have a vehicle, the Orion capsule. We have a rocket, the SLS. And right now, as we speak, they are in simulators. They are in pools. They are training. For those who've lost track of the mission numbers, Artemis II isn't the landing, right? We aren't kicking up dust yet with this specific flight.
Correct. Artemis II is the Apollo 8 of our time. It is a crewed flight test. They are going to launch, fly to the moon, loop around the far side, going further into deep space than any human has been since the 1970s, and then come home.
Why loop? Why not just land if we have the rocket and the capsule?
Because you have to test the car before you drive it cross-country. This is a brand new spacecraft. That is the critical difference between Apollo and Artemis. Apollo was a race. It was a sprint. We went, we planted the flag, we grabbed some rocks, we left. Artemis is about staying.
Building a base.
Eventually. It's about building a station in orbit around the moon called Gateway. It's about figuring out how to extract water from the lunar ice at the poles to make rocket fuel and breathable air.
It's the difference between a camping trip and building a cabin.
That is the perfect analogy. And to build that cabin, you need to solve problems we didn't really have to worry about in 1969, like food.
I saw that in the notes. NASA back for seconds on Food System Design Challenge.
It sounds like a cooking show, but it's deadly serious.
Because if you're going to Mars eventually, which is a 3-year round trip, you can't just pack 3 years of TV dinners.
No, they're too heavy. Launching mass into space is incredibly expensive. And also, the nutrients degrade over time. If you eat a 3-year-old vitamin bar, it might not have any vitamins left in it.
So you need to grow your own.
You need to grow it, you need to process it, you need to prepare it. So NASA is asking the public for help, for innovation. How do you create a food system that is low mass, low waste, uses minimal water, and keeps the crew happy and healthy?
Because food is morale.
Food is huge for morale.
Ah,
If you're eating gray paste for 500 days, you're going to have a mutiny on your hands.
true. I get cranky if I skip lunch. I can't imagine skipping good food for a year. And the crew, when they do this loop around the moon, they're going to experience something profound.
They are.
The Earthrise perspective.
The overview effect. Seeing the Earth as a marble, a fragile blue and white marble hanging in a vast black void, it changes people. Every astronaut who has seen it says it changes how you view politics, borders, the environment.
A perspective we could probably use a lot more of right now.
Desperately.
Speaking of long road trips and changing perspectives, let's go to Mars, our robotic friend Perseverance, or Percy as the team calls it.
The geologist on wheels.
There is a specific update here from just a few days ago, February 2026, that I think is huge, but it might get buried under the flashy human spaceflight stuff.
I agree.
Perseverance Rover completes first AI planned drive.
This is a watershed moment for robotics. Not just for space, but for robotics in general.
Explain why. I mean, my Roomba navigates my living room and mostly does a good job Why is it such a big deal for a billion-dollar rover to drive itself?
Because your Roomba doesn't have a time lag.
The speed of light problem.
Right. Mars is far. Depending on where Earth and Mars are in their orbits, a radio signal can take anywhere from 5 to 20 minutes to get there. One way.
So a 40-minute round trip for a command.
At worst, yes.
Right.
So you can't joystick the rover. You can't play it like a video game. If you see a cliff coming up on your screen at mission control, the rover arguably fell off it 10 minutes ago.
So how did they do it before this AI update?
Micromanagement. Painstaking, agonizing micromanagement. The engineers on Earth would get a 3D image from the rover's cameras, stare at it for hours, identify every single rock.
Every single rock.
And plot a very specific, very safe path. They'd upload a command like, go for 1 meter, turn 10 degrees right, stop. Then they'd wait 40 minutes to see if it worked. A good driving day might be moving 20 or 30 meters.
That sounds excruciatingly slow.
It is. And it limits the science you can do. If you spend your entire day just trying to drive to the next interesting rock, you aren't drilling rocks or analyzing samples.
And now, with this AI-planned drive...
No, the dynamic is different. They give Percy the destination. Go to that ridge over there. And the rover uses its onboard AI, its own brain, to look at the ground in front of it, identify hazards, that rock is too sharp, that sand looks too soft, and calculate its own path in real time.
So it's making its own choices.
It has agency. It has autonomy. It means the rover can drive significantly farther in a single Martian day because it doesn't have to stop and ask for permission every 10 feet.
It's like watching your kid drive off to college. They're making their own decisions now.
And we need this technology. This isn't just a cool upgrade for Mars.
What do you mean?
Think about those ocean moons we mentioned earlier, Europa or Enceladus. If we ever send a submarine to an ocean under miles of ice on Europa, the signal lag is even longer.
And the signal might be blocked by the ice itself.
Exactly. You can't remote control that. The robot must be able to think for itself. It must be able to say, I see an obstacle, I will avoid it. Or even, I see something scientifically interesting that my human controllers didn't know was here, I will stop and study it.
So Perseverance is the prototype for the future of all autonomous exploration.
Exactly. It's learning to walk on Mars so that future robots can run and swim across the solar system.
That is incredible. Okay, let's look up. We've been on the ground, on Mars and the moon. Let's talk about the eyes in the deep, the great observatories. We have the veteran and the rock star.
Hubble and Webb.
The dynamic duo of astrophysics.
That they are.
I feel like every time a new telescope launches, people write Hubble's obituary. Oh, Webb is here. Hubble is done. But looking at the feed from this month, Hubble sees galaxy with dark rings. It's still working.
It is absolutely still working, and it's still crucial. We need to understand that they do different things. They're not competitors. They're collaborators.
How so?
Webb is an infrared telescope. It sees heat. It's designed to see the very first, most distant galaxies. Hubble sees primarily invisible and ultraviolet light. It sees what our eyes would see, but much, much better.
So they complement each other.
Perfectly. Hubble is the historian of the solar system. It's been watching Jupiter's Great Red Spot for decades. It's the one that tells us how the storms are shrinking over time. It gives us the long-term context that Webb, being new, can't provide yet.
It has the baseline data.
Exactly. And visible light tells us things that infrared can't, and vice versa. It's like having two different kinds of senses to perceive the universe.
Speaking of Webb, the notes highlight a specific piece of science, detailing the formation of distant solar systems, and they use this metaphor of a baking recipe.
Yes, this is where Webb just blows everything else away. It can peer through cosmic dust.
Why does that matter?
Because new solar systems, new stars, and planets are born inside vast, cold, dense nurseries of dust and gas. To Hubble, in visible light, those nurseries look like opaque walls. The famous pillars of creation, for example. You can't see what's happening inside.
The dust gets in the way.
But Webb looks in infrared, which is heat radiation, and that light passes through the dust. So for the first time, we can see the baby stars and the disks of planet-forming material swirling around them right as they're being born.
And the baking recipe.
Webb uses an instrument called a spectrograph, which breaks light down into its component colors like a prism. And in that rainbow, there are fingerprints of different chemicals. It can tell us, hey, that planet-forming disk has water vapor, it has carbon monoxide, it has methane.
So it identifies the ingredients that are available to build new planets.
Exactly. And by looking at thousands of solar systems that are forming right now, we can start to piece together our own history. We can say, oh, so that's how the water probably got to Earth. Or that's how a planet like Jupiter got so big so fast. We were watching the process happen elsewhere to understand how it happened here 4.5 billion years ago.
It's like looking into other people's kitchens to figure out how your own cake was baked.
That is the perfect analogy. And sometimes we find that other kitchens are using very, very different spices.
Which brings us to what might be the biggest mind bender of this whole report, the exoplanets.
The frontier.
We talked about our solar system's census. 8 planets. But the galactic census is exploding. The number is now over 6,000 confirmed exoplanets.
6,000 confirmed worlds orbiting other stars. And just remember, 30 years ago, that number was 0.
0!
We suspected they were there, but we had no proof. Now we know the galaxy is teeming with them. It's probably the case that most stars have planets.
But here's the headline that really caught my eye. The weirdest solar system we've found so far. You may be in it.
That is the provocateur in the data. That's the real paradigm shift.
Unpack that for us. We all grew up thinking our system was the model. Rocky planets on the inside, gas giants on the outside, nice, mostly circular orbits, standard issue, IKEA furniture for the cosmos.
It's the anthropic bias. Yeah. We think we're normal because we're the only example we knew. We are here, therefore this must be what a normal system looks like.
But now we have 6,000 other examples.
Now we have a huge sample size, and we're realizing we might be the weirdos.
So what are the other neighbors like? What are these other systems doing that's so different?
We see things that, according to our old models, simply shouldn't exist. The most famous example is the hot Jupiter.
Hot Jupiters.
These are gas giants, planets as massive as Jupiter, or even more so. But they are orbiting their star closer than Mercury orbits our sun.
Wait, what?
They're whipping around their star in a matter of days, not years. Their atmospheres are being boiled off into space. They are scorched worlds.
That violates the frost line rule we just talked about. You said gas giants have to form out in the cold where the ice is.
Exactly. So finding them was a shock. It suggests that planets don't always stay where they're born. They move. They migrate. A Jupiter can form far out and then spiral inward, wrecking everything in its path on the way in.
And our Jupiter
stayed put. Or at least it didn't spiral all the way in, which is probably a very good thing for Earth.
And we also see a ton of super-Earths.
Yes, this is maybe the biggest surprise. The most common type of planet we're finding out there is a size we don't even have in our solar system. Planets larger than Earth, but smaller than Neptune. Super-Earths or mini-Neptunes.
We don't have one.
We don't. We have Earth, which is rocky, and then we have this huge gap, and the next thing up is Neptune, which is 17 times the mass of Earth. We are missing the most common type of planet in the galaxy.
So our orderly street, with the nice spacing and the polite planets in their lanes, is actually a rare anomaly.
It's certainly looking that way. It's possible that a calm, stable solar system like ours is the exception, not the rule. And if a calm solar system is required for complex life to evolve over billions of years,
then life might be rare.
Or life might just be very adaptable and can exist in these crazier systems. We don't know yet.
Yeah.
But it certainly makes you appreciate our specific arrangement. We have a Jupiter far enough out to act as a gravitational shield, deflecting comets.
Right.
We have a sun that is remarkably stable. We have a large moon that stabilizes our axial tilt, so we have regular seasons. It's a lot of things that had to go just right.
It really makes the neighborhood metaphor feel different. We aren't just in a suburb, we might be in a historic preservation district, a gated community.
Protected heritage site, yes.
I want to touch on one more thing from the notes before we wrap up. I saw a lot of mentions of citizen science.
Yes, this is so important.
We talked about the millions of asteroids and the thousands of exoplanets. It turns out NASA isn't finding all of these alone with supercomputers.
No, absolutely not. The data volume from these surveys is too high. We are drowning in data, in a good way. We have more images and light curves than professional astronomers can possibly analyze.
So they have these projects like Zooniverse, where regular people, you, me, the listener, can log on and look at the data and spot things.
Absolutely. The human eye and brain are still better than any algorithm at spotting weird patterns or subtle changes. There are high school students who've discovered new planets in the TESS satellite data by noticing the tiny dip in a star's light.
That's amazing.
There are retirees who have cataloged thousands of craters on Mars or classified galaxies from Hubble images. It's real, valuable scientific contribution.
That is incredibly empowering. It means the census isn't just something we read about, it's something we can actually contribute to.
It democratizes the cosmos. You don't need a PhD to be an explorer anymore. You just need an internet connection, a bit of patience, and curiosity.
I love that. So let's try to summarize our metropolis, this whole crazy, beautiful system.
So,
Okay, so we live in a system dominated by a massive magnetic tyrant, the sun, that holds 99.8% of all the mass.
and provides all the energy that makes everything else possible.
We are surrounded by 1.3 million ancient bricks, the asteroids, and nearly 300 active, diverse worlds, the moons, some of which might be hiding vast, warm oceans.
An archipelago of potential habitats orbiting the giant planets.
We are actively training to leave our house and build a cabin in the backyard via Artemis, and we have autonomous robot dogs sniffing around the park down the road. That's Perseverance on Mars.
And through our telescopes, we're looking over the fence at 6,000 other houses, the exoplanets, and realizing our own house is built to a very unique and perhaps very rare blueprint.
It's a lot to take in. It's overwhelming, but in the best possible way.
It is. But that's the beauty of it. The more we look, the bigger and more interesting the universe gets. The horizon just keeps moving further away.
So here's my final thought for you, for the listener, the provocation, if you will. For most of human history, we used to look at the night sky and see a ceiling, a dome with lights painted on it.
The celestial sphere, solid and unchanging.
Now, based on all this data, we know it's not a ceiling. It's a deep, three-dimensional, chaotic ocean, and we are just learning how to swim.
We've barely dipped a toe in the water. We're still standing on the shore.
So tonight, if you get a chance, go outside and look up. Don't just see the dots. See the depth, see the traffic. Think about that robot driving itself across the red sands of Mars right now. Think about the ice shifting on Europa's hidden ocean.
See the potential. And realize you are part of it. You're made of the same stardust.
Thank you for diving deep with us into this. It has been a trip.
It's always a pleasure to tour the neighborhood.
And remember, all the data we discussed is based on NASA's factual records as of February 2026. The universe changes fast, so keep watching.
Keep wondering.
Clear skies, everyone.